Welcome to this explainer, where we are going to decode exactly what Cambridge examiners are looking for in mathematics syllabus 9709, specifically targeting topic 4.4. We're talking about Newton's laws applied to connected particles, pulleys, and Towbars. I'm your host, and today we are looking at the ultimate Cambridge exam strategy. We're calling this one the street artist, because it's all about making your mark with bold strokes of creativity, but absolutely backed by a rock-solid underlying structure. To kick things off, I want you to picture a real Cambridge mathematics past paper scenario. Let's look at a classic paper, right? The clock is ticking down, there's less than 20 minutes left, the tension in the exam hall is palpable, and we have two typical students taking this exam. Let's call them Alex and Sam. Now, Alex is our walking encyclopedia. Alex overloads his paper with raw mathematics facts. He's writing down every single formula related to Newton's laws, but with absolutely zero contextual analysis. Just a massive brain dump of equations. Then we have Sam. Sam is a different story. Sam rushes. Sam sees a diagram of a pulley, goes into total panic mode, skips reading the command word requirements entirely, and just starts mashing numbers into a calculator hoping for the best. Fast forward to results day. Both of them lost massive marks on this question. Why did they fail? Because they didn't understand the underlying strategy. They didn't understand how to decode the examiner's actual intent. Today, we are going to fix those exact errors. We are going to transform those harsh red pen marks into beautiful green check marks, and we are going to build your ultimate blueprint for exam success. Okay, let's look at our roadmap for today's session. We'll start with the connected particle strap, move into core theoretical foundations, break down the procedural framework, highlight critical examiner warnings, and finally, look at evaluative thinking for top marks.
Section 1. The connected particles trap.
So we have to start here, because this trap catches literally thousands of students every single exam season, and that includes our students Alex and Sam. Why do students consistently lose marks on pulleys and Towbars? It is a vital question. If you read the Cambridge Principal Examiner reports, which you should absolutely be doing, by the way, they consistently cite topic 4.4 as one of the most universally misunderstood areas in the entire mathematics syllabus. Now, you might be sitting there thinking, well, it's just F equals ma, right? Force equals mass times acceleration, how hard can it really be? But the examiner's data tells a completely different story. Students are not losing marks because they can't do basic algebra. They are losing marks because of how the questions are formulated and how they fail to recognize the structural demands of the prompt. Before we dive into the exact reason why this happens, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCS to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, let's get into the mechanics of this trap.
The real trap here isn't the math itself. It's the inability to take a known physics concept and apply it when the exam presents a completely unfamiliar scenario. This is exactly where Alex's strategy completely fell apart. Remember, Alex is our memorizer. Alex memorized the tension equals mass times gravity in a basic static hanging string system. But the exam didn't give him a basic static string. The exam introduced a towbar, connecting a car and a trailer, moving up an inclined plane, with a very specific, separate resistive force acting on each vehicle. The moment Alex sees that, he panics. He just writes down generic formulas that don't apply to accelerating systems on a slope. The examiner wants to see you adapt. If you cannot extract this specific data from a unique context, for instance, recognizing that the tension in a towbar is acting in opposite directions, pulling the trailer forward but pulling the car backward, your generic math facts won't save you. You have to analyze the context.
Section 2. Core theoretical foundations.
To escape that trap of unfamiliar contexts, we need to look right behind the curtain at what the examiners are actually actively measuring. You aren't just being tested on whether you remember the formulas. You are being evaluated across three distinct cognitive domains: knowledge, application, and analysis. Let's break this down. First, you define the principle. That is your knowledge and understanding. For example, explicitly stating the assumption that the acceleration of two connected particles on a taut, inextensible string is identical. You have to know that. Second, you execute the analysis. That is your application. This is where you build your simultaneous equations, applying Newton's second law to each particle separately. And third, you draw conclusions. This is the analysis domain, and it's where Sam failed miserably. Sam failed because Sam rushed past the command words. If a command word says, "show that," you cannot just write the final answer. You must provide every single logical step in your mathematical argument. This is where we use the Peel framework: point, evidence, explanation, link. You make your point about the forces, you provide the evidence through your equations, you explain the mathematical steps clearly, and you link it back to the command word's specific requirement.
This quote from the Principal Examiner report is absolutely crucial. Candidates referencing cross-topic connections achieve significantly higher marks. What does this mean for you? It means that integrating Newton's laws with other areas of the syllabus acts as your secret weapon. The examiners are explicitly telling you that when you connect topic 4.4 with, say, kinematics, using your constant acceleration formulas, your Suvat equations, alongside your force equations, your mark potential absolutely skyrockets. They want to see that you understand the mathematics ecosystem as a whole, not just isolated formulas. If you can find the acceleration using kinematics and then plug that acceleration into your F equals ma equation to find the unknown tension, you are demonstrating a master-level understanding.
Section 3. The procedural framework.
Let's move to the practical side. How do we build a system that guarantees you hit all those assessment objectives? By strictly following this standardized 5-step sequence. This is what we call the method mark strategy. You are rewarded for your systematic process, not just your final numerical answer. Let's put our rushing student, Sam, through a quick rewrite challenge to show you how this transforms an answer. Step 1. Deconstruct the question. Sam now stops and highlights the exact command word. Let's say it's calculate. Step 2. Extract relevant data. Sam systematically identifies and lists the mass of the car, the mass of the trailer, and the driving force. Step 3. Select the analytical framework. Instead of panicking, Sam realizes we need 2 separate equations of motion, one for each particle, rather than treating them as a single combined system, because the specific question asks for the internal tension in the towbar. Step 4. Execute with clear notation. This means using a capital T for tension, a lowercase a for acceleration, and defining positive directions clearly. Step 5. Present with correct terminology, stating the final answer to 3 significant figures with the correct units of newtons. By using this blueprint, that entire messy paragraph of rushed math Sam originally wrote just transformed into a clean, structured, undeniable mathematical proof.
And this brilliantly illustrates a core truth of Cambridge exams. Your structured working is just as vital as your calculator output. The method mark strategy is your absolute safety net. Let's say the pressure gets to you and you accidentally punch the wrong number into your calculator at the very last second of the exam. It happens. But if your systematic processing is on the page, if your simultaneous equations are set up correctly, if your annotations are clear and logical, the examiner will award you the vast majority of the marks for your method. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to at @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Secure those method marks by showing your process.
Section 4. Critical examiner warnings.
Even with a solid procedural process, there are massive red flags you must actively avoid. Examiners repeatedly flag these 3 exact mistakes year after year. This means you can instantly gain a competitive advantage simply by double-checking your formatting and your context alignment. Let's run an interactive workshop right now. Challenge 1, the data scan. I want you to visualize a complex data source. Imagine a diagram of a rough inclined plane. There is a pulley at the very top. Mass A is resting on the rough plane. Mass B is hanging freely off the side. The string connecting them is inextensible. Friction is present on the slope. In a real exam, you have about 60 seconds to scan this and extract the core trend. What is the defining force that dictates the direction of motion for this entire system? Think about it. If you immediately identified that you need to compare the component of mass A's weight acting down the slope against the hanging weight of mass B, you nailed it. Using the wrong approach here, like completely forgetting to resolve the weight of mass A into its parallel and perpendicular components using sine and cosine, is literally the #1 mistake examiners see. You have to scan the data and find the hidden forces.
Seeing these 2 approaches side by side proves exactly why generic answers fail. Context is everything when evaluating connected particles. This brings us to challenge 2, find the flaw. I'm going to read you a paragraph of working from our student, Alex. I want you to spot the exact sentence that is losing him marks. Here is Alex's working. The system accelerates, so F equals ma. Therefore, driving force minus resistance equals total mass times acceleration. Tension is found by mass times gravity. Did you catch it? The flaw is that final sentence. Tension is found by mass times gravity. That is a context-free, generic physics assumption for a completely static string where nothing is moving. In an accelerating connected particle system, the tension is absolutely, unequivocally not just mass times gravity. To find tension in an accelerating system, you must isolate one single particle. Identify all the forces acting just on that particle, and use the resultant force equals mass times acceleration to find the specific tension.
The examiner's commentary screams about candidates making this lazy assumption every single year. Context is everything.
Never assume the examiner knows what you mean. Clear definitions anchor your causal relationships, and they prove your underlying knowledge. This brings us to Challenge 3, speed writing. You have 30 seconds. How would you quickly explain what the term smooth pulley allows you to do in your mathematical calculations? Let's use our Peel framework here. If your mental answer looks something like this, a smooth pulley means there is zero friction at the peg or axle. This allows the mathematical assumption that the tension in the string is equal and constant on both sides of the pulley. If you wrote that, then you just secured your method mark. That is the exact, precise presentation convention the examiner is hunting for. Don't just skip over words like smooth, light, or inextensible. They are mathematical permission slips that tell you exactly how to set up your equations.
Section 5, Evaluative Thinking for Top Marks.
Finally, let's explore how to push your grade into the absolute highest possible tier. The higher-order assessment objectives require this 4-step comparative analysis to show that you can evaluate alternatives and justify your recommendations mathematically. Let's look at a classic, tough scenario. Let's say a question asks you to evaluate 2 different towing models: towing a trailer with a rigid, solid tow bar versus towing it with a flexible tow rope. Step 1, you must identify the similarities. Both of them transfer a pulling forward force, and you must identify the differences. A rigid tow bar can provide a backward thrust when the car is braking, whereas a flexible tow rope will simply go slack and offer no resistance. Step 2, you use comparative connectives like whereas or conversely to structure your argument. Step 3, you support it with mathematical evidence, showing through your equations that a negative tension calculation actually implies a physical thrust force in a tow bar. And Step 4, you draw a definitive conclusion about which model maintains control of the trailer during rapid deceleration. This isn't just math anymore. This is high-level, critical engineering analysis.
The absolute top-tier students don't just calculate blindly. They act like actual mathematicians, evaluating the structural integrity of the problem itself. They consistently demonstrate 3 specific traits. First, they question the given assumptions. If the problem says the plane is smooth, they explicitly note that friction is 0. Second, they consider different conceptual perspectives. They ask themselves, what happens to the system if the string snaps? What are the new initial conditions for the separate particles? And third, they justify every single decision with hard mathematical evidence. They don't just guess, they prove it. Look at Alex and Sam now. By adopting this framework, Alex stopped relying on generic facts and started analyzing the actual context. Sam stopped rushing, decoded the command words, and used PEL to structure his math. They evolved from struggling candidates to top-scoring strategists.
Layering your exam answers through these 3 distinct levels, descriptive, analytical, and evaluative, transforms a standard average response into a professional, undeniable demonstration of skill. This is your mathematics success blueprint. This is how you guarantee top marks. You use the command word decoding to know what to do. You use the Peel framework to structure how you do it. And you use a time management matrix to ensure you have the 60 seconds you need to actually scan the data before you start writing. You have to put the reps in. You have to train your brain to recognize unfamiliar contexts instantly.
So here is the final question for you. Will you rely on just trying to find a numeric answer, or will you use our procedural framework, comparative connectives, and evaluative thinking to absolutely guarantee every single method mark on your next past paper? Students who implement these exact mathematics strategies see an average improvement of 2 full grade boundaries. But that only happens if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Take this examiner's playbook, apply these rigid rules to your next study session, and watch how those complex pulley problems turn into your biggest scoring opportunities. Drop a comment below right now with your target grade for mathematics and the biggest challenge you're currently facing. Our team reads and responds to every single comment. Like and share this video with your study partner. Ace the Exams. Your Cambridge success starts here. Keep studying smart, and I will see you in our next explainer.